In this set of lessons, I'm going to be going through the formula sheet for the NCEA 3 statistics exam at the end of the year. There is a set number of formulae that they'll give you, so it really does behoove you to know what these formulae are, when to use them, and really the mechanics of how you would use them. It also helps as well to know what they don't give you. So with that said, let's start with the permutations and combinations. This is the first part of the exam formula they've given to you, and they're represented by this rather scary set of equations here that look intimidating, but they're really not. Permutations with a P is represented by this one here, also with the P, and C combinations are represented by that set there. What's the difference? What are they? The permutations is the number of ways that we can order things if the order matters. So we care what order things are done in. We would use a permutation. So the way that I remember it is that permutations are picky. They're picky about the order that things are done. Combinations are when we want to find the number of ways that things can be counted or collected if the order doesn't matter. Okay. And both of these have a little asterisk, and that asterisk means that there is no replacement. So once we put something in order, we can't use it again. So if we have the three letters, say A, B, and C, how many ways can we put those three letters together? We can't say A and then A again and then B. We can only use A once and only once. So why is this important, and why is it part of probability? Remember that the probability of an event happening, if all events are equally likely, is the number of ways something can happen divided by the total number of possible outcomes. So combinations and permutations are ways that we have of working these two things out. You'll see what I mean when we come to do the examples. So the first thing that looks pretty scary here that you may not have seen before is this notation, N exclamation mark. And that doesn't mean that we are shouting the letter N really loudly. What that means is that we have N times N minus 1 times N minus 2 times dot dot all the way to 1. So 3 factorial would be 3 times 2 times 1, and the 1 is a bit superfluous, and we stop. So 3 times 2 times 1 is, of course, 6. What would that mean? Okay, let's go back to our example. Let's say we have the three letters A, B, and C. How many ways are there of ordering those three letters if the order matters? There's A, B, C that we've got there. There's also A, C, B. There is B, A, C. There is B, C, A. There is C, A, B, and C, B, A. And it's going off the page. And that's all of the examples if we use all of them. And if you look here, there are 1, 2, 3, 4, 5, and 6 of them. So we would use just n factorial by itself if we want to find the number of ways of ordering n number of objects if we use all of them and the order matters. So why would we use this if we can just do a list? A few years ago, one of my students asked me if I had 11 players in a cricket team, how many orders of batsmen or batters could we have? And he spent hours working it out. But there is a quick way of doing it. It's 11 factorial. Now, 11 factorial, if you look at it there, it's going to get big really quickly because you've got 11 times 10 times 9 times ... all the way to 1. And I can't be bothered doing that. So this is when we would use our calculator. So let's grab our calculator. So here's the Casio calculator that most students use in the exam. And the way that we get factorial and in fact permutations and combinations are like this. We would go option. Now sometimes these options are already at the bottom, but if they're not, you hit the option OPTN, go across to probability, which is F3, and you'll see that they're loaded right there. So this is x factorial, so some number factorial. This is NPR. We're going to work out what these mean in a second. NCR. So these formulae that are in the formula sheet are preloaded into your calculator. But sometimes you need to rearrange it, so it's always good to know the mechanics of how it works. Okay. Let's work out, if we have 11 players, how many ways are there of ordering our batting lineup? If there's 11 players in a cricket team, 11 factorial is going to be a huge number. So this kid who was trying to do it by hand, good luck, because there's what? 39, almost 40 million ways of doing that. All right, let's look at ways we could use this n factorial notation. So 8 students are being arranged in a line in a school photo. All students are different. Well, okay, I hope they are. How many different ways can the 8 students be arranged? So for this, we've got a set number of students. The order matters. We're going to use all of them, so we're going to use our n factorial. So 8 factorial is going to be what? And we're going to grab our calculator, and we're just going to enter 8 factorial, exe, 40,320. Oops, 40,320. Okay. B says 4 of the students are in the same debating team. How many arrangements are possible if these 4 students must stand together? So for B, there's still 8 students, but 4 of them are together. So we need to do permutations separately. So here are our 4 students who are in the same debating team. It's a pretty realistic drawing of these people. This guy doesn't have a head, doesn't have a neck. How many ways are there of arranging the debating team? That's going to be 4 factorial. So that's going to be 4 times 3 times 2 times 1. So it's 12 times 2 is 24 different ways. So once we've got that 24 different ways, we've got 4 more students. So let's do the students who aren't in the debating team in red. Now, these 4 are together, but they could be here, here, or here, or I guess even here. So really, these count as 1 student. So what are the number of ways of Whoops, actually, I've just created a new student out of nowhere. That was sloppy. Where are those students going to go? They're going to be treated as if they're a single student. So the 4 students and this lot of 4 which are together, it's really going to be 5 factorial ways of arranging those 5 objects. And 5 factorial is going to be 5 factorial 120. Whoops. 120 different ways. So there are 120 different ways of arranging these 5 objects, but one of those objects can itself be arranged 24 different ways. So the number of ways in total is going to be 120 times 24. And I have no idea what that is off the top of my head. Times 24. 2,880, which is a lot. Okay, so now we're told that 2 of those students, I guess we're saying that we don't care about the debating team now, Aria and Ben do not want to stand at either end of the line. How many arrangements are possible? So all of them have to be on the line, but neither Aria nor Ben can be at each end. Okay. The way that we're going to do this is we're going to find all of the ways that there are of arranging, ignoring Aria and Ben for now, which is going to be 8 factorial. Okay, so 8 factorial is going to be a number that we've already worked out, 40,320. Okay, now how many ways are there of Ben being at either line? If we take Ben out of the equation, there are 7 factorial possible combinations, but Ben can be at one end or the other end. So we're going to say that the ways that Ben could be at the end of either of those lines is 7 factorial times 2, which is another really big number, times 2, 10,080. Okay, but Aria is in the same boat. So there are 10,080 ways that Aria could be at each end. Have we got it? Can we just subtract this from this? Not quite, because what about the ways that both Aria and Ben could be at either end? If Ben is at one end and Aria is at the other end, the students in the middle, there are 6 of them. So the way that could be done is 6 factorial ways. And 6 factorial is 720. But there's 2 ways of doing it. If Ben is on one end and Aria is on the other end, we could do it as well that Aria is on one end and Ben is on the other end. So it's going to be another 720 taken away. So the total number of ways that we can rearrange these 8 students in such a way that Ben and Aria are not in the middle, are not on the end, is 40,320 minus the 10,080 for the ways that Ben could be at each end, minus the number of ways that Aria could be at the end, and we are going to add 720 and 720, because remember these 720 are going to be subsets of this one. So our grand total is going to be a pretty big number. So it's going to be 40,320 minus 10,080 plus the number of ways that Aria could be on one end and Ben on the other end, plus the converse of that. So the number of ways that there are of arranging those students is 21,600. So let me go through that again. We worked out how many ways there were in total of finding the 8 students, of ordering the 8 students. And then we said, okay, so how many ways are there of arranging those students if Ben is on one end? And then we doubled it because he could be on the other end. And then we did the same again for Aria. And then we said, okay, but that doesn't take in, that also includes the ways in which Ben and Aria were on either end. So we would need to put those back in so that we didn't. So remember, combinations are when the order does not matter. So how can we read these equations here? NCR, you would say this, N choose R. So N is the total number to choose from in the group. And R is the number that you are going to pick. Okay? And remember, there is no replacement. So once you pick one of them, you can't pick it again. It would be nice if you're playing rugby and you could pick 3 Richie McCaws, 2 Dan Carters, 4 Jonah Lomus. You can't do that. There's only one. All right. Let's have a look to see how this would work. So let's go back to our earlier example with A, B, and C. So A, B, and C. How many pairs can we make from that? We can make A, B. We can make A, C. We can make B, C. And that's it. There are only 3 pairs that we can make. Because remember, the order doesn't matter. So CA is already done here, AC. So we can't do that. Okay, let's have a look to see how that would work if we just did the algebra. So we're just going to use this equation up here. So N for this would be 3. And R would be 2. So that tells us that, I'm just going to move this down a wee bit. This tells us that when we come to work it out, the number of pairs is going to be equal to 3 choose 2. And if we wanted to work that out, it's going to be 3 factorial, so 3 times 2 times 1, divided by n minus r factorial, which is 1 factorial, which is going to be 1, times r factorial, which is 2 factorial, which is going to be 2. So 3 factorial is 3 times 2 times 1, divided by 1, times by 2 times 1. And 3 times 2 times 1 is, of course, 6. And 1 times 2 times 1 is going to be 2, which is 3. So there are 3 possible pairs, and that's exactly what we did when we did it by hand. So now let's look at a bit more complicated example, but not really that much complicated. Say we have 12 people in a group, and we need to choose 5 of them to do a task. How many combinations are there? The first thing we need to ask is, does the order matter? And the answer is no. As long as we're just choosing 5 people, any 5 people would do. So our n for this, the total number that we've got to choose from, is going to be 12. And the r that we're going to be choosing is going to be 5. Now, If you did this by hand, it's going to be kind of gruesome. You're going to need to do 12 times 11 times 10 times over 7 times 6 times 5 times 5 times 4 times 3. You're not expected to do that realistically. Your exam's 3 hours long, and it's not really a contest of how quickly you can do multiplication. So we would grab our calculator. So we would go to this key here. There are 12. We're going to choose 5. So there are 792 different combinations that we can choose 5 people. All well and good. Let's say that we've got 5 people and we want to know how many. We can divide this up into groups of 5, groups of 4, or groups of 3. So as long as we have either 5, 4, or 3 people, we're fine. How many of these groups can we possibly make? We know how many it is for 5. It's 792. How many is it of 4? It's going to be 12C4. And I don't know what that is off the top of my head, but let's use the calculator just to get in the practice of doing it. 495. So you see how it drops away quite remarkably. There's quite a big difference between 495 and 792. But just for completion's sake, let's do it in lots of 3. So 12, choose 3. And now at less than halves, it goes to 220. So how many in total would there be? We would need to add those together. So 792 plus 495 plus 220 gives us 1,507. Which is a random number. You wouldn't really be able to work that out in your head. And if you did it by hand, finding 1,500 different combinations. So when the order does matter, we're going to need to use permutations. So the order does matter. All right, the first example we had, we said we've got 3 things, and we're just going to call them A, B, C. How many permutations of 2 can we make? So now the order matters. So let's list them. Let's do all the ones where A comes first. So A and then B, and then A and then C. Let's do all the ones where B comes first. B comes first and then A. Remember, these are different. A, B, and BA. They're the same thing if we didn't care about the order, but now that we care about the order, it does matter. And then we've got BC, and now we need all the things where C comes first, CA and CB. So there are 6 different combinations if the order matters. Remember, when we did combinations, there were only 3, because a combination AB is the same as BA, AC would be the same as CA, and CB and BC would be the same thing. But here it really does matter. All right, let's have a look to see how many different permutations there would be if we had our 12 people and we wanted to put them into groups of 5. How many groups of 5 could we make if the order of those people mattered? Now, N is going to be 12, R is going to be 5, and it's going to get pretty gruesome there. So I'm just going to go straight to the calculator now. Let's get our calculator. So 12 permutation 5. There's going to be a lot. 95,040. That's a lot. And if you remember in our combinations, we have a look at our combinations, there were only 792 and 92. So there's a big difference between 95,040 and 792. So permutations grow a lot faster. Okay, then we said let's take that, and now let's work out how many there are for 4 people. So we have our 12 people, we choose 4 people. So this is going to be 12p4. And again, I'm just going to go straight to our calculator. And we see another really drastic drop. Still a lot though, 11,880. So when we have permutations, do not do it by hand. Use your calculator and know how to do it, because those numbers will get really big really fast. And then for completion, we said, okay, how many trios can we make of this? If we have 12 people and we pick 3 of them, 1,320. 1,320. So all up, there were 95,040, 11,880, and 1,320. And I have no idea what that is. So 95040 plus 11,880 plus 1,320. And now there's over 100,000 different combinations to choose, permutations to choose from, 108,240. By the way, you have to be careful, like I'm trying to be. There is a difference, of course, between a combination and a permutation. It's in normal language when people talk, the terms permutation and combination are pretty much interchangeable. But for us, no, they're not. Look at some examples. So we're told that a school has 10 runners, 6 are seniors, 4 are juniors, and there are 4 runners chosen, and the order that they run in matters. All right. How many different ordered relay teams can be formed? Looking at this, they say that the order matters, so it's going to be a permutation. There are 10 runners, that's 10 to choose from. So this one here, for if we're finding seniors, let's have a look. It's going to be seniors and juniors. All right, how many different ordered relay teams can be formed? So I guess we don't care whether they're seniors or juniors in this case. So this is going to be a permutation. So it's going to be 12, pick 4. Any 4 will do, but the order does matter. So 12p4 is going to be a number. I think we've already worked it out though, haven't we? 12p. No, not 12p. It's going to be 10p. 10p4. I thought that looked familiar. 10p4. So let's clear that. 10p4, 5,040. Let's change that to 10. So the first one is going to be 5,040. So how many ordered relay teams have exactly 2 seniors and 2 juniors? If you have a look at this one, does the order matter? The order doesn't matter when we first find them, but at the end we're going to have to find the number of ways that these combinations fit. So we're going to need to do these separately. So we have 6 seniors and we want to choose any 2 of them. So 6 choose 2 is going to be 6 choose 2, 15. So there are 15 pairs of seniors that we can choose. For the juniors, it's going to be 4 choose 2, which is going to be a little bit easier, I think. 4, choose 2. So there are going to be six different pairs that we can use. So all up, there are going to be 15 times 6 numbers of pairs all up. So there are going to be 90 different groups or 4 runner groups. Now these groups have to be sorted out in order. So once we have those 4 in the group, how many orders of those in any 4 of those groups can we find? That's the order does matter, but we're using all of them. So the answer for that is going to be 4 factorial, which is 4 times 3 times 2 times 1, which is 12 times 2, which is 24. So we've got 90 groups, and each one of those 90 groups, there are 24 different ways of sorting them. So the final answer for that one is going to be 90 times 24, and I don't know what that is off the top of my head. 90 times 24, 2,160. So now we get the slightly more difficult question. If an ordered relay team is chosen at random, so it's out of all of them now, so we can forget this one. What is the probability that the first and last runners are seniors and the second 2 runners are juniors? So now we have a probability. So the probability, let's do this, the first and fourth are seniors and the second and third are juniors. Remember, any probability like this, it always has a numerator and a denominator. So how many possible teams are there? There are 5,040. Now we need to find how many meet that criteria, where the first and the fourth are seniors and the second and third are juniors. Now you might be thinking, oh, how are we going to do that? But it's not actually as difficult as you might think. So let's have a look at the first and the second, the first and the fourth from the seniors, I should say. Well, there are 6 to choose from. So for the first one, there are 6 to choose from. And the fourth, when we come to choose the fourth one out of that lot, there's only 5 left. So there are only 30 different ways of doing that for the seniors. Okay. For the juniors, there are only 4 juniors. So when we come to choose the second runner, there are 4 to choose from. And then when we come to choose the third number, there are only 3 to choose from. So that's going to be 12. So in total, the total number of ways that we've got of doing this are going to be 30 times 12, which is a number that I can't work out off the top of my head. 30 times 12, I should know it. 360. So there are 360 different permutations that meet that criteria. So the probability is 360 over 5,040. And if we wanted that as a decimal fraction, it's going to be 0.71. 0.71, let's go 3 decimal places. 0.071, it's already at 3 decimal places. And I wonder if we could get this to a nicer number. So let's go 360 over 5,040. Is it going to go to a nice number? It is 1 over 14. if we wanted it as a simplified proper fraction. In this question, we're told that a Year 13 committee has 13 students, 7 from House A and 6 from House B. A panel of 5 students is selected. How many panels contain exactly 3 students from House A and 2 students from House B? Does the order matter? The order doesn't matter. It's just any 3 from House A and any 2 from House B. So it's going to be, there are 7 students in House A, and we don't care about the order, so it's got to be a combination, and we want to choose 3 of them. Then from House B, there are 6 students, and we choose either any 2 from there. So 7, combination 3, 7, choose 3 is going to be 7, choose 3. There are going to be 35 different combinations in House A, and then when we choose 2 from House B, there are going to be 6 students in House B. We choose any 2 of them. There is going to be 15 in there. Now, do we add them or multiply them? No, we multiply them because they're independent events. 35 times 15, so the total number is going to be 35 times 15, which is going to be a number. So there are going to be 525 different ways of doing that. 525. How many panels contain at least 1 student from each house? How are we going to work that one out? Let's work out how many in total there can be. So in total, there are 13 students, and we want to choose 5 of them. So if we ignore how many there are of where they come from, how many in total could there possibly be? It's going to be 13, and then we're going to be choosing 5 from there. So 1,287. All right, now we want to work out how many there are from just one. What's the probability of getting none from one of them? So let's say that we choose how many had none from House A. Well, in that case, for House A, we would have 7, and we would choose none of them. And that means that in the other one, we would have 6, and we're going to be choosing 5 of them. So just run that in your head. So this is the number of ways that we can choose no students from the first group, House A. The way that we can choose no students from House A, there's only one way of doing that, and that's just choose none of them. And then all of them, 6 choose 5, is going to be a pretty low number. So 6 choose 5, 6 choose 5. There are going to be 6 ways of doing that, which kind of makes sense because if we're choosing 5 out of 6, all that's going to matter is that which student are we going to drop. So 1 times 6 is 6. Okay. Now let's say that we choose all of them from group A and none from group B. So now it's going to be 7 choose 5 times 6 choose 0. And again, there's only one way that can happen, and that's just to choose none of them. So 7 choose 5 is going to be a little bit more than 6. So 7 choose 5 is going to be 21. So that's there are 21 ways of choosing all the students from A, and there are 6 ways of only choosing all of them from house B. Were 1,287 that we started with, and we're going to take away 21 from that one, and we're going to take away 6 from that one. And what that is, I don't know. So 1,287 minus 21 minus 6 is 1,260. So 1,260 different combinations where we have at least one from all of the houses. Okay, now we're told that a panel must have exactly 3 from A and exactly 2 from B. From the panel, a chairperson from house A and a secretary from house B are chosen. How many possible outcomes are there? If you have a look, we already worked out how many meet that criteria. So now we have to work out how many to choose from there are in house A and house B. If we have 3 from house A, there's only 3 ways that we can do that. Either we can choose 1, 2, or 3, which is actually the same as 3 choose 1. So there's going to be 3 different ways of doing that. And for the second one, it's going to be house. There's only 2 there, so we've got 2 and we want to choose 1. That's going to be 2. So there are 3 ways of doing the first way and 2 ways of doing the second way, and there are 500 out of 525 for each of them. So the total number of ways is going to be 525 times 3 times 2, and that's the total number of combinations. What that is off the top of my head, again, I have no idea. So 525 times 3 times 2 is 3,150. So 3,150 different ways of choosing 3 from A, 2 from B, and the chair comes from A and the secretary comes from B. Okay, I think that should do for now. Any questions, let me know in the comments. I'm always willing to go through any of these questions again in a video if you want me to. All right, good luck.